Testing. Hello and welcome to the video. So this is a fairly involved question involving the maximum weight of an elevator, but it reflects some calculations that are pretty appropriate for real-world type situations. So here we're looking at an elevator in a health club, and they told us, I guess, they're looking at only men here, perhaps for the same reason as we saw in an earlier example, that will be the heavier group of people. So if the elevator can carry a full load of men, it should be able to carry a full load of women. Alright, so they give us some information, and let's just summarize that a little bit. They tell us the weights of those men is normally distributed with mean 181 and standard deviation 31, so we can write that. And they told us the elevator is limited to 33 occupants, so our sample size is 33. So this is for the population, keep in mind. For a sample of size 33, that standard deviation would be divided. Let's take a look at question 1. Assume there are 33 men in the elevator. What's the average weight per man beyond which the elevator would be considered overloaded? So to solve this, we'll take the max weight. It's overloaded if it's more than 6,435 pounds, and divide it by the number of people on the elevator, which was 33. So if we do that out, 6,435 divided by 33, we get 195 pounds. So if the average weight per man on the elevator is 195 pounds or less, we'll be under the weight limit, but if it's more than 195 pounds, we'll be over the weight limit. Not good news for the people on the elevator. Alright, next part of the question. What is the probability that one randomly selected male health club member will exceed this weight? So we're talking about a single individual from the population, so we can use this information here, right? It's a sample of size 1, essentially. So if we draw out our density curve, it's a normal with mean 181, standard deviation 31, so we can fill in that 181 right there. And we want to know what's the probability one man exceeds that limit. The limit was 195, so really what we're calculating here is the probability that x is greater than 195. So there's 181. Our standard deviation is 31, so if we go to one inflection point, we're already out at 210, so 195 somewhere around here. We want to know the probability that a single man, chosen at random from all the people at the health club, would have a weight above 195 pounds. From our picture, we can see it's not that area. For a normal curve, it's a value of interest. We can calculate the area by using normal CDF.
And then we input the mean, 181, the standard deviation, 31. Oh, excuse me. That's not what we do first, right? Hopefully you're looking at that thing. We'll need those numbers, but not yet. When we do, the first value we want to put in is the left-hand value for our area of interest. So we're going to put in 195. And then the right-hand value, which is infinity, so on our calculator that's 1E9. And now we want that mean of 181 and the standard deviation of 31. Alright, so let's go ahead and calculate that on our calculator. We'll do second vars, normal CDF, and then 195, comma, 1E9, comma, 181, comma, and then 31, and we calculate that out, and the value we're getting there is 0.32577, which rounds to 0.3258. So if we pick a single individual male at random from this health club, there's like a 33% chance that he's going to be above that 195 weight. So let's fill this in here as a decimal, 0.3258. This could seem like bad news, right? Because the average weight has to stay below 195 pounds a person on a full elevator, or we're in trouble, right? We're over the weight limit. So that's what the next part of this question asks. It says, all right, well, there's a 33% chance that one individual will be over the weight limit. If I fill up that elevator with 33 people, what's the chance that that the average will be exceeded? So now we're really looking at that same picture as before, but what's changed, now we have a sample of 33. So we've got n equals 33, so when we draw out our normal curve now, the mean is still 181, but the standard deviation, it used to be 31, now it's 31 divided by the square root of 33. See how that standard deviation shrinks so quickly as the sample size increases. 31 divided by square root of 33. That's coming out to be about 5.3, just for your reference. 5.39, so 5.4. So let's draw it out here. Here's my mean at 181. The standard deviation is 5, so now that inflection point is representing about 5 more than 181. The inflection point is 186. Go out another inflection point. We're going to have to make our tail longer here, right? So it would be about, so 195 is going to be somewhere way out here, just a tiny little wedge out here. And we need to know what is this area. So we're going to do normal CDF. And the left-hand boundary is 195. The right-hand boundary is 189. The mean is still 181. The standard deviation is 31 over the square root of 33. So let's go ahead and enter that. Second vars, option 2 for normal CDF. We've got 195, 189, 181, and then 31 divided by the square root of 33. That gives me 0.0047. As a percentage, that's less than 1%. Interesting, right? To notice that for a single individual, there's a 33% chance of them being over 195 pounds. For a group of 33 people, there's less than a 1% chance that the average weight would be above 195. That's because for a group of people, right, yeah, we might have a few that are above, but we'll probably also have a few that are underweight, and it will balance out. In order to have the average of the group be, more than 10 pounds above the population average, we'd have to have a lot of people, most of the people in that group, be overweight and none be underweight, which would be unusual. Things tend to balance out. All right, let's pull down. We got two more parts of this problem. So now they say if the elevator is full on average 4 times a day, how many times do you expect the elevator will be overloaded in one non-leap year? All right, so now we're going to say, okay, here's the probability that it's overloaded on any given day. Let's figure out how many times a day it's going to be full. And I'm sorry, I need to correct here. It's the probability it will be overloaded if it's full on any given day. So first, let's find how many times a year is the elevator full. Well, the question tells us 4 times a day. The non-leap year, that's 365 days a year. So the elevator is full 4 times 365 times a year. So 4 times 365 gives us 1,460 times a year that the elevator will be full. On any given time that it's full, the probability it's overweight is 0.0047. So if we multiply that 1460 times the 0.0047, that tells us how often we expect the elevator to be overloaded. And the answer we get there, 6.82. 6.862, it says round up to the nearest unit. So we would say 7. We would expect it to be overloaded about 7 times a year. So even though there's a very small chance it's overloaded any given time it's ridden in, if it's at capacity, it gets ridden at capacity so often in a year that we would still expect it to be overloaded 7 times a year, which is really not such great news for the elevator or the people in it, right? We don't ever want it to be overloaded. So if we look at the last part of that question, this was such a long question I had to put it on another sheet of paper, so let me pull that up. If we look at the next part of that question, it says, is this reason for concern? Well, I would say yes. It's not adequate to ensure the safety of the passengers. 7 times a year, that elevator is going to exceed the capacity. So that's a problem. They need to go back to the drawing board and increase the capacity level for that elevator to make sure that we don't expect it ever to reach beyond its capacity.